So we're going to do talk about atoms, molecules, and ions. And so let's start with back in the day, students had it really easy. They only had to know 4 elements: earth, air, fire, and water. Obviously, this is not the periodic table that we're familiar with. But back, thousands of years ago, they didn't really have any idea even what an atom was. However, in 400 BC, a gentleman by the name of Democritus hypothesized the existence of small little particles that he called atomos, which obviously is where the word atom comes from. So it was hypothesized thousands of years ago, but it actually wasn't very verified until maybe about 100 years ago by someone you may be familiar with, a man by the name of Albert Einstein. So we're going to look a little bit at the intro to the atom. We'll talk a little bit about the the atomic theory, and some of the stuff you may have remembered from or you may recall from elementary school. So here's an important individual in understanding atoms and the atomic theory, a gentleman by the name of Lavoisier. He discovered that in a chemical reaction, you don't lose any mass. So for instance, let's say we take carbon and oxygen and copper, and we put them together to make a new compound. What happens in this case is you make something you can see called copper carbonate that has all 3 things in it: copper, carbon, and oxygen. But what's really interesting is the amount. So for instance, if I take 10 grams of carbon and 40 grams of oxygen and 53 grams of copper, if we add that all up, that gives us 103 grams of something called copper carbonate. So what you'll notice is that if we add up the mass, so let's say that this is like the left side, and then that's the right side. If we add up the mass on the left side and we compare it to the mass on the right side, you'll notice that they're exactly the same. So the left side mass equals the right side mass. And what he said when he realized this, he came up with a concept, a really important concept. It's called the law of conservation of mass, which basically says that the mass of the reactants is equal to the mass of the product. So we do not lose any mass in a chemical reaction. So if I take, for instance, let's say I take hydrogen and I mix it with oxygen and I get water, then the formula for water is actually H2O. It's hydrogen and oxygen. The amount of hydrogen and oxygen would equal the amount of water, okay, because no mass would be lost. That's a really important concept in the development of the atomic theory. Another important concept is this: proportions of atoms. So in this picture here, what you're seeing is a formulation, actually the reverse. It's the taking water and breaking it up into hydrogen and oxygen. And if you think what we just talked about was take hydrogen, take oxygen, and you put them together, you make water. The reverse is true. I can take water and I can split water into hydrogen and oxygen. Okay, and that's actually the opposite of what we just looked at. And that's actually what you're seeing here. This is something called electrolysis, where electricity is being used to split water into hydrogen and oxygen. So here, for example, on the right, you'll notice a molecule of water. So we said that if you take hydrogen and you take oxygen, it gives you water. The reverse is the breakdown of water. That's what you're seeing here. Okay, and electrolysis. Now, what's really interesting is the proportion. You'll notice that in every water molecule, there's the same ratio of hydrogen to oxygen. There are 2 hydrogen for every 1 oxygen, right? 2 hydrogen, 1, 2 for every 1 oxygen. If you break down water into hydrogen and oxygen, you'll also notice that because there's 2 hydrogen for every 1 oxygen, you'll notice that the amount of space taken up by the hydrogen gas is about double the amount taken up by the oxygen gas because of the fact that there are 2 atoms of hydrogen for every 1 atom of oxygen. And that actually is the law of definite proportions. Okay? Another important concept in chemistry. So that's 2 now. First concept is that whenever you have a chemical reaction, you don't lose any mass. All right? The other concept is that when you do make compounds or you break them up, there's a ratio between the atoms that's always the same. Okay? So for example, something like salt, sodium chloride. All right, the ratio of sodium, so sodium is Na and chlorine is Cl. The ratio is always 1 sodium for every 1 chlorine. Okay, that's really, really important concept. Okay, so the atomic theory was then put together by a gentleman named Dalton in 1766. Sorry, that's when he was born. I'm not sure exactly when he put the theory together, but it was based on previous results like the law of conservation of mass and definite proportions. And this is what he, putting that information together, this is what he came up with. And again, going back to Democritus's idea, Dalton put together the concept of the atomic theory, which is basically that matter is made up of small little particles called atoms. All right, this goes back to Democritus's idea. The atoms of an element are all identical. So for example, if I look at hydrogen, in this case, the hydrogen atoms are identical to each other. So like this hydrogen atom is identical to that hydrogen atom, and that oxygen atom is identical to that oxygen atom. But the hydrogen and the oxygen are different because they are different elements. So they are identical for the same element, and they're obviously different for different elements. Okay, so number 3 says different elements have different atoms. So number 2 and number 3, you can see in this picture that if they're the same element, the atoms are identical, but if they're different elements, the atoms are different. You can see it visually in this picture. From previous result, we know that when the atoms do combine, for instance, to make water, they combine in whole number ratios. This is important, whole number ratios. In other words, it's like 2 to 1 or 3 to 2. If I look at hydrogen peroxide, which is H2O2, it says that I need 2 hydrogen for every 2 oxygen. So the ratio is 2 to 2 or 1 to 1. These are whole number ratios. You can't have 1.5 to 1 because you can't have half an atom, right? They can only be whole number atoms. So 1 atom, 2 atoms, 3 atoms, 4 atoms, and so on. And then number 5, based on Lavoisier's work, that you can't lose mass. It just says that whenever you have a chemical reaction, all you're really doing is just rearranging the atoms. You're not creating them, you're not destroying them, because the mass is the same. So if I make water, all I'm doing is rearranging hydrogen and oxygen and putting them together in a new combination. Okay, so this is called the atomic theory. Any questions in the chat in regards to this? That's okay. All right. If you have any questions, just put them in the chat. Unfortunately, that's the only way we're going to be able to do this. Okay. So the next, leading, or continuing from this concept is this, the particle theory. Now, this I think is something that you probably did do in elementary school. The particle theory looks like the atomic theory. If I compare the two, like kind of side by side, you know, the first part of the atomic theory says all matter is made up of atoms, right? This says all matter is made up of tiny particles. So instead, you know, instead of using the word atoms, we're using the word particles, okay? So that looks the same. If I look at statement 2 and 3, it says all particles of one substance are the same. Different substances have different particles. I mean, that is exactly what the atomic theory says, right? Number 2, all atoms from the same element are identical. Atoms from different elements are different. So that's the same. Where the atomic and particle theory differ, because in number 4 and 5, it talks about the ratio in a formula, and it talks about rearranging. You can see 4 and 5 are different. So 1, 2, 3 are actually the same, but 4 and 5 is different. So particle theory says that all these particles, these atoms, basically, they're always moving around. So they're never stationary, okay? And they actually move faster. So they'll move faster if the temperature increases. So, and the reverse is true. They'll actually move slower if the temperature decreases, okay? The fifth point of the particle theory says that the particles, there's a force of attraction between the particles. So then if we think about, for instance, something like salt, which is NaCl, the sodium atom and the chloride atom are like attracted to each other, so they form a compound. And the closer they are, the stronger those forces would be. You know, and this is true for water, H2O. However, you can actually split them up. So you just have to exert a pretty strong force to split them up, but they can be split up. Okay. So if I compare the atomic theory and particle theory, they're almost the same, but they're not exactly the same. There are differences between them. Okay. Like I said before, the atom was actually not proven until the 1900s. And that's because, I mean, they're so small, you can't see them. And it's, you know, people need to see to believe. So it wasn't until Einstein actually proved that they actually existed. Basically, he observed something called Brownian motion, which is here, which when he was looking at things, it was a proof of concept that if you look at water under the microscope or things in water, they're like moving around. They're moving around, right? And the question he thought, why are these things in water moving around? What's making them move? So his idea was that what's making these particles in water move are water molecules that are moving around. And what they do is they bump into these particles in the water. And by doing that, the particles move. So even though he couldn't really see the water molecules, he knew they must be there because something had to be making the particles in water dance around. That's Brownian motion. So these particles that were in water are moving around, they're vibrating back and forth, and he realized that something must be hitting them, and that was his proof. Okay. Obviously, he didn't see them, but he was smart enough to realize that this must be the reason, this must be the proof for the existence of these little particles called atoms. It wasn't until you get like really powerful microscopes, electron microscopes, you can actually see the presence of the atom. Okay. Any questions so far about the atomic theory? So if you have any questions, just put it in the chat. Okay. Obviously, we had some issues, so we can talk about that later. All right. Okay, so then let's move on. Sorry. Okay, so that's a little bit of the history, but what I want to do right now is I want to actually turn my attention to the actual atom itself, okay? The parts of the atom. So an atom is a particle. It's the building block of an element. So like, for example, like gold, right? We're familiar with gold. Gold is made up of gold atoms. Aluminum is made up of aluminum atoms, right? So in the particle and atomic theory say that all the gold particles, all the gold atoms are the same. All the aluminum atoms are the same. And aluminum atoms are different than gold atoms, right? That's what we just kind of talked about. But what exactly is the atom? All right, so we'll look at right now. So the atom itself is made up of 3 parts. All right, the first part is called the electron. It's not really the first part, it's just the first part on the slide. That's the electron. That's the part that whizzes around the atom. So if we think about the atom kind of like the solar system, the sun would be the nucleus. Okay, and around the nucleus, around the sun, we know they're planets, those would be the electrons. They're whirling around, kind of like Earth whirls around the sun. The nucleus, which I said is like the sun, is the home for the 2 other particles, what are called the protons and the neutrons. Okay, these 2 are about the same size in terms of their mass. So protons and neutrons are about the same size. Electrons are really, really tiny. They're about 2,000 times smaller than the other 2, which is important because when we do like how to figure out how heavy an atom is, we actually don't even consider the electron. We only consider the protons and neutrons. So what I mean by that is, if I look, for instance, so one of the things that I will get you to look at is building an atom, so you can visually see. Girls, can you see the screen? Someone put in the chat that you can see it or not. Okay, good. All right. So the one of the things I will get you to look at is, what exactly, what does it look like? Okay, so it's we're gonna get a chance to play with something called Build a Sim. So that would be right here. Oh, where's my? So it's called Building an Atom Using PhET. Okay, so this is the activity that you guys can play around with. And so that would be this one right here. Okay. And one of the things that you'll get a chance to play around with, and so you can visually see what an atom looks like. So for instance, here's what's called my periodic table. Okay, I can make hydrogen. So there is hydrogen. It even tells you as soon as you put this in, these are my 3 subatomic particles: protons, neutrons, and electrons. Now, you can only make the first 10 elements on this table. So that would mean you can make hydrogen, helium, all the way up to something called neon. So like, for example, if I dump all the protons in here, you can see every time I add a proton, it becomes a new element. That's actually important because it tells you that the proton is actually what identifies the element. So like, for example, right now I have fluorine. Fluorine has 9 protons. I just dumped 9 protons into the center, into the nucleus. What makes fluorine different than neon is actually just the number of protons. You can see that neon has 10 protons. The nucleus contains the protons and the neutrons. So for example, in this case, if I just dump these neutrons, so right now I have in here, you can see an equal number of protons and neutrons, right? Now, if I look at the mass number, you'll notice the mass number reads 20. Now watch what happens if I add electrons. You'll notice the mass doesn't change, right? The number of electrons doesn't affect the mass because they're so light, we actually kind of just ignore them. So what I'm putting together for you right now is actually what something like neon would look like. So neon will look something like this. All right, you can see that it's made up of the 3 subatomic particles: protons, neutrons, electrons. And you can see the nucleus, which is the center of my atom, only has the protons and neutrons, and you can see the electrons on the outside. Now, in reality, these things would be moving around because particle theory says that, it's not stationary, it's moving around. So the electrons will be moving around. Even the nucleus itself would be vibrating back and forth. Anyway, so I'm going to give you a chance later on to play with this so you can actually make your own atoms. Okay? It's a neat chance, like a good opportunity for you to be able to see this. All right? Any questions in the chat about this? Okay. So if I reset this, and we'll do another one together. Let's say we want to make let's say, for example, this is hydrogen, and this is helium, okay, which is the second, you can see it's highlighted here. It's just the second element on the periodic table. It has 2 protons. Let's see, if I add 2 more neutrons, the mass number is 4. You'll notice that right now it actually says it's positively charged. I'll explain that in a second, okay? So right now you'll notice that it's neutral. Okay, so what a neutral atom is, so they need a certain, yes, that's right, they need a certain number. The question is, do you need a certain number to make an element? Yeah, so the number of protons will determine the element it is. So it's actually pretty simple. The first element only has 1 proton, second has 2, third has 3, fourth has 4. Okay, and you'll see that when you're playing around with this. So here are my 3 subatomic particles. Again, you'll notice the nucleus only has neutrons and protons. You'll notice the electrons are on the outside. The electrons, again, do not contribute to the mass number. This says that it's neutral. So what that means is that if I have an equal number of electrons and protons, the atom is neutral. If I add an extra electron, you'll notice it becomes negatively charged. So I can actually show the charge, the negative. If I take the electron away, let's say now it's neutral. If I take another one away, you'll notice that it's positively charged. So atoms can lose and gain electrons. You can see then if they're an equal number of electrons and protons, the atom is neutral. But if we take away electrons, so if we take away 1, you see it's positively charged. It's neutral, and I add 1, you'll notice now it's negatively charged, okay? So a negatively charged atom is one that has extra electrons, and a positively charged atom is one that has missing electrons, okay? Questions from the chat? It says, what is the difference between positive and negative and positive? Okay, so let's take a look at beryllium, okay? Let's make beryllium. So beryllium is the 4th element. So it's going to need 4 protons, okay? Usually the number of neutrons is kind of close to the number of protons. There's actually a way to figure this out, which I'm going to explain in a minute, okay? So right now you'll notice that it has 4 protons and only 3 electrons, and the charge is positive. So when is something positive? Something's positive when there are more protons than the electrons. The reason for that is because the protons, if I go back to this, the protons actually have a charge. So the protons are positively charged. Let me make that bigger so you can see it. So protons are positively charged, neutrons are neutral, and electrons are actually negatively charged. And you can see that here. So watch what happens. So when we add the another electron. So right now, if we look at the count, there are 4 protons. So they are each has a positive charge. So we'll call that +4. And there are 3 electrons, each with a negative charge. We'll call that -3. You can see there's more positive than negative charges, so it's positively charged. If I add an extra electron, now these two numbers are the same, so now my atom is neutral. Okay. If I have more electrons, then my atom is negative. You can see it's now negatively charged. So then a negatively charged atom has more electrons than protons. A neutral atom has the same number. And a positively charged atom has less electrons than protons. Okay, that help? So you'll get a chance to play around with these. Okay. All right. So then these 3 subatomic particles were all individually discovered. The first one were the electrons. They were discovered here. This is an apparatus showing you the discovery of the electron. These are what we call cathode ray tubes found in like old TVs. What you're seeing here is a beam. You see this beam that's being deflected? These are actually beams of electrons. Now, what they realized when they were looking at these beams, you can see them over here too, is that the beam gets deflected and attracted towards the positive side and away from the negative side. So what that told people was that if you're, I don't know if you've studied electricity, but things that have the same charge, if they have like charge, a like charge would be like positive and positive, would repel. Negative and negative would repel. If they have the opposite charge, then they actually attract. So positive and negative would actually attract. So whatever this was, this beam was obviously attracted to the positive side, and you could see was being repelled by the negative side, which told us that whatever is in this beam had to be negatively charged. Okay? Because of the physics. Yeah, if it's negatively charged, it would explain why it's attracted here and why it's repelled there. So this was actually the first discovery of the electrons as negative particles. So let's move on. Let's take a look at then. So that was the discovery of the electron. Now and this is the actual setup. This is the individual who actually discovered the electron, J.J. Thomson. Okay, this is the setup, and you can see the beam being. So there's the beam is so the red beam would be if there was no like negative and positive plate setup. It would just travel in a straight line. But as soon as you set up positive and negative charge, the beam would be attracted, you see, to the positive side, because the beam is actually made up of negative charged particles. Okay. Now the nucleus was actually discovered by a scientist named Rutherford. What he did was he took really thin layers of gold, and he fired radiation through the gold. Now, the radiation were actually helium particles, okay, or atoms of helium. And what that is, if you go back to the sim, an atom of helium is 2 protons and 2 neutrons. You can see that with 2 electrons. Now, what they used in the experiment were alpha particles, which are basically helium particles, something that would look like this, okay? And what happened was, and that's what these little things are. So these are the helium particles that were being fired, okay, through the gold. So this, imagine that this from here to here is a layer of gold, okay? And we know gold is made up of gold atoms. Now, what they noticed was that when they put the radiation through the gold, most of the radiation, which are really just particles of helium, okay, most of the radiation went right through. You can see it goes right through, right? But once in a while, the particle would be like deflected or maybe even bounce back. So what's going on here? I mean, if this is gold, if all of this is gold and is made up of gold atoms, and if you fire radiation, which are made up of particles, through the gold, and most of it goes to the other side, what does that tell you about the actual material? Well, it tells you that most of the material is actually empty space. Which means the atom itself, because if gold is made up of atoms, and most of the stuff is getting through the gold, that means that most of the atom is just simply empty space. So if I have a picture of an atom, I have a tiny little nucleus, very, very tiny, and most of the atom itself. So imagine this sphere is, for example, the atom. Most of that would be just simply empty space. And that would explain why most of the radiation was able to get through. Because if these little yellow, imagine these yellow spheres represent my gold atom, you can see most of it would be empty space. So if I were to shoot an alpha particle, which is a helium atom, through the gold, the chances are it would go right through, because you can see the nucleus is really tiny, so the odds of hitting the nucleus are very, very low, which explains why most of the time the particle went right through. Okay. Okay, so we talked about the atomic theory, the particle theory. Right now we're looking at the actual atom itself, the 3 parts of the atom. It's mostly empty space. The nucleus is quite tiny. We know the nucleus only has neutrons and protons, and the electrons are on the outside, like planets. We can just do a little bit more with the atom. We can actually talk about some very important things that you will see when you look at what's called the periodic table, which is something that we'll look at a little bit more in detail later on. And it actually comes up in this simulation. So for example, here, if I look at, for instance, this is, for example, let's say we make lithium, okay? Lithium, you can see, is the 3rd element in this periodic table. It has, in this case, I'm going to make it with 3 protons and 4 neutrons, okay? So there's my lithium nucleus. You'll notice that there's no electrons, so it's positively charged, okay? So I can add my electrons to make a neutral, and I know that when they're the same number, it's neutral. So there you go, it's neutral now. You'll notice it has no charge. Okay, so it's neutral here. And now, you'll notice that there's a symbol, right? So the symbol, which is right over here, has generally three things that we want to look at. One is the symbol of the element's name. So lithium is actually abbreviated Li. It also has two other things. One is you can see the two numbers, 7 and a 3. So I'm going to talk about what these two numbers actually mean, okay? Now, you can see that here. So here's an example. Here's carbon. All right, so carbon is abbreviated with the symbol C. And you can see there's two numbers. There's a 6 and a 12. All right. Now, what these numbers refer to, you can see here, the 6 refers to something called the atomic number. All right. And the bigger number, which in this case is 12, refers to something called the atomic mass. Okay. So you have the symbol, and you have the atomic number, and you have the atomic mass. Okay. So the atomic number is simply just the number of protons. All right. The atomic mass is actually the mass of the nucleus, which is actually the number of protons and neutrons. Okay. So, and if you go back, for example, to the this example with lithium, okay, you'll notice that we have the nucleus of lithium has 3 protons. You can see top right corner is 3, and there's 4 neutrons, right? So the atomic number is 3. Now, in this case, the atomic number is actually on the bottom. You can see it right here. It's actually on the bottom. And the mass number is actually on top. And that's important to note because some periodic tables will have the smaller number on top. Some will have it on the bottom. So it's really, really important that you keep that in mind. But the mass number is always the bigger number, okay? And then you can see in that case, it's 7. Now, if you look at the nucleus of lithium, you'll notice that there are 7 particles. There's 1, 2, 3 protons, and 1, 2, 3, 4 neutrons. Okay, that adds up to 7. If I look back at this example here, you'll notice that there are, now, just round it off. So we're going to say it's 12. The nucleus has 12 particles in it, 12 protons and neutrons. We can build this so you can see it. So for example, that's beryllium with 4 protons, boron with 5, carbon with 6. That's 6. So then if you add 2 more neutrons, that would be 6 also. Now, so let's take a look at this, okay? So now we have carbon atom, right? So you see the symbol is C. The atomic number is 6. Again, remember the atomic number is the smaller number. It could be on the bottom, it could be on top. In this case, it's on the bottom. In this case, it's on top, okay? So, and the mass number is 12. So the mass number is the number of protons and neutrons in the center. So if I look, I have 6 protons and I have 6 neutrons, which adds up to 12. All right. So once again, the mass number is the combined number of protons and neutrons. The atomic number is just the number of protons. Again, you'll also notice right now the charge is positively charged because I have more protons than electrons. So for me to make this neutral, I'll have to add electrons. You can see if I make it 6, it's neutral, because if it's the same number of electrons and protons, it's considered neutral. Okay? All right. So just to summarize, the atomic number is the number of protons. The mass number is protons and neutrons. And the atomic charge is basically, it's neutral if the number of protons and electrons is 0, okay? So let's look at like a couple of examples, all right? So for instance, here we have N. So N stands for nitrogen. So this would be nitrogen, all right? And you can see that there are two numbers. So the mass number is always the bigger number. So in this case, you see the mass number is 14. And the atomic number is actually 7. Okay? Now, remember, the atomic number is the same as the number of protons. So the number of protons is also 7, because these two are the same. Now, if it's neutral, let's assume that this is neutral. Let's assume all these are neutral, okay? Then, if it's neutral, we also know that the number of electrons is also 7, okay? That's if it's neutral, okay? We're going to assume that this is neutral, all right? Now, so we have, remember, 3 subatomic particles. There's protons, right? There are electrons, and the third one is the neutrons. So how many neutrons would this have? Well, the mass number is 14, and that is the sum of the number of protons and the number of neutrons. So if we do some simple math, the number of neutrons would be the mass number minus the number of protons. In this case, it would be 14 minus 7. So the number of neutrons is 7. Okay, that's the example for nitrogen. So you can see its atomic number is 14. Its mass number is 14. The atomic number is 7. So we can use that to figure out the number of protons, 7, electrons, 7, and neutrons, 7. Okay, let's look at another example. Let's look at fluorine. Okay, so fluorine is got the symbol F. All right. So a quick word about symbols. Generally, it's the first letter of the element, but not always. So I'll show you, with the next one what I mean by that, but not always. So the symbol for fluorine is F, and you can see its mass number is 19. So let's just reuse this setup. Okay. Let's just reuse all this. So the mass number of fluorine is 19. Okay, its atomic number is 9. Right? Remember, mass number is the bigger number, right? The mass number is 19, which we know then the number of neutrons is 19 minus the number of protons. Okay, so what's the number of protons? Well, the atomic number is the same as the number of protons. That's what the atomic number is, number of protons. We're going to assume this element is neutral. So for now, the number of electrons is equal to the number of protons. Okay. The number of neutrons is the mass number. So the bigger number minus the smaller number. So that would be, in this case, the number of neutrons is 10, because 19 minus minus 9, right? So that will give us 10. Okay, so that's an example with fluorine. The next example is iron. So, and you'll notice that iron, the symbol for iron does not start with an I. It starts with Fe because it's the Latin name sometimes that's taken, or the symbol is taken from the Latin name of iron. And you'll eventually recognize some of these symbols as we go through them. Okay. What I did in this case, I actually put the mass number on the bottom, so you'll notice the bigger number now is on the bottom. But again, it's the same idea, right? So the idea is that the mass number is the bigger number. So in this case, let's just use this template again. Okay, so the mass number is 56. The atomic number is 26. Okay. We know the mass number is the number of protons and neutrons. We talked about that before. So the number of neutrons is the mass number minus the number of protons. So 56 minus the number of protons. We know the number of protons is the same as the atomic number. So that's also 26. So when neutral, these two are the same. So then we can work out the number of neutrons as the number, the mass number, sorry, minus the number of protons. So 56 minus 26, which would give us 30. Okay, what is a 3? Well, it looks pretty bad. And where do we answer this question? What is the number of protons, neutrons, and electrons if neutral? We know that the number of protons and neutrons is the mass number. And if neutral, the number of electrons is equal to the number of protons, which is what we've been doing here, okay? Okay, so what you then can do is you could try a couple things on your own, and then on Friday, we will meet back and continue with the atom. So you could try the activity. It's called Build an Atom Using PhET. So it's an instruction sheet that talks about what to do here. And then there's some questions you can answer, including questions about when the particle is not neutral, which we talked a little bit about. So you can try that. And then here, there is a worksheet that's called the atomic structure. So what this worksheet is it goes over what we just finished up right now, where you have like the substance and the symbol number, and then you have to fill in the charts. So for example, if you have the atomic number and a mass number, what are these three things? And you assume that these are all neutral, okay? So we know the mass number is these two things, protons and neutrons. We know the atomic number is the number of protons. We know the number of electrons is equal to the number of protons. And we know the number of neutrons is simply the mass number minus the atomic number, right? So you can use those formulas to figure out the missing information, and on Friday we could take this up. Okay, so why don't we stop there? Why don't we stop there, and then that's it. I will